Okay, I'm turning on the camera such that you can see me in case I want to gesture a little bit. So thank you all for joining. A few words for introduction. So I'm Sabrina, I'm from the University of Kassel, and we have one Cusco student here, but as, he's not here right now, but he left us for Paris. So like a few weeks ago, we had 3 Cusco students here, and right now we have none. But I still have some people sitting here in the room, so in case you hear some sounds from the background, don't be surprised. A little bit for me, so I'm not part of the Cusco project, but I'm working on a project which is quite similar. So I'm usually working with Rydberg atoms in the context of quantum metrology and quantum simulation. And there we have some collaborations with the Collège de France in Paris. But today I'm going to talk about quantum Zeno dynamics. And this is not my main research topic, but in my research topics I always came across quantum Zeno dynamics. So in both my topics, the metrology and the simulations, I had to do with the quantum Zeno dynamics. So I'd like to give you an introduction on quantum Zeno dynamics today, or more general also the quantum Zeno effect, and we will see what else effect there are. So please interrupt me in case you have any questions in the meantime. And otherwise we can start. So I know there's like a lot of different motivations on how to start and introducing the quantum Zeno dynamics, and I thought I'd take a slightly different route than what you might have already heard. Namely, I want to start with an easy example of everyday life. So imagine you're going for a walk, maybe in a nice park, or maybe or maybe on a cemetery or something like that. Some people might fancy that. And then you see this statue. So it's a statue of a weeping angel. And you look at the statue, it looks super nice. Then you turn around and look back and you have the feeling it might have moved a little bit. And actually you think, yeah, okay, that's not possible, that cannot happen. Then you turn around, you want to walk away, but then you hear a sound behind you, and then you turn back, and then you see that. So you see the statue moved actually and wanted to attack you. And I must admit this did not happen to me personally, and I'm very happy about that. But for the Doctor Who fans amongst you, you might recognize this picture of the weeping angels. So as an explanation, these are monsters which can just move when you're not looking at them. So as long as you look at them, they can't move and they can't attack you. So the best tactic to fight a weeping angel is actually do not blink. So you look at them, and there's this quote from Doctor Who, which is, don't blink, blink and you're dead, don't turn your back, don't look away, and don't blink. Good luck. So it turns out that the quantum Zeno effect actually made it into science fiction. And I now want to explain you a little bit how you can actually fight weeping angels using the quantum Zeno effect or quantum Zeno dynamics. And in the very beginning, I want to start with a bit of history about the quantum Zeno effect. So the Zeno effect was actually a paradox which was stated by Zeno from Elea, who was an ancient Greek philosopher who was born in 4088 before Christ. And back then there were different philosophies very leading, and one of them was from Pythagoras, who said that everything is in change and the world is becoming and everything's moving. But then there was this counter movement by Zeno, who said that motion and change are mere illusions and that motion is just a trick by our senses given to us. And therefore he made 3 different paradoxes, or he stated 3 different paradoxes to prove that actually motion cannot be possible. And one of the famous paradoxes is the arrow paradox, which is also related to the quantum Zeno effect. So it goes like that. He assumes there's an arrow and you shoot an arrow. And he says that everything, when it occupies in an equal space, is at rest. So it means you have an object and it's having this part of the space, and as long as it occupies this part of the space, it cannot move because it's occupying this kind of space. Then the next step is, when you have an object in motion, then at each point of its motion, it occupies this part of space. So that means that you can part the trajectory of the object into different parts where it's addressed at every second. And that means that the flying arrow is therefore not moving at all. Yeah, that was my Dropbox, sorry. That the flying arrow is therefore not moving at all. So he stated that because it is resting at each point of its trajectory, it cannot move at all. So that was one of his paradoxes, and maybe you also heard about another one, which is Achilles and the tortoise, where he says that Achilles can never catch up with the tortoise because every time he wants to catch up, he has to pass the distance before that the tortoise passed in the previous time interval. So there are several paradoxes that he stated to show that actually motion is an illusion and that nothing is moving at all. So of course, in the classical physics, that is not what happens. So we know that an arrow moves. When I shoot an arrow, it will definitely arrive at the target. But still, it was quite a difficult task for the people to explain this paradox. So what was actually the flaw in this logic? So why is it not working? And it turns out that many great thinkers thought about this problem, and that most or a lot of modern mathematics is based on this kind of problems, and that his arguments actually made the foundations of modern mathematics. Now the thing is, even though it's a paradox and it's not working in the classical world, it turns out that it is actually possible in the quantum world. So the first paper about that was published in 1977, and it's called the Zeno's paradox in quantum theory. And it states that the quantum Zeno paradox, the Zeno paradox, should be possible in quantum theory. And I think the paper is quite amusing because it has this charm making fun of cats all the time. So for instance, this is some quote of the paper, and it says, will the cat escape the cruel death awaiting it, against which it has no defense, provided its vital signs are constantly watched with loving care? So it's quite amusing to read the paper. And in the paper, they're actually saying that it is quite bizarre and physically unacceptable what happens in this paper, or what happens in the Zeno paradox, and this limit of the very frequent measurements, as we will see in a minute. So they weren't, I think, not quite convinced yet if this is really working or not. And then in 1990, there was the first experiment which really could record the quantum Zeno effect. And it was published by the group of Wineland in Boulder. And they published the paper based on a proposal which was published 2 years before. And it is based on trapped ions, which are driven with short RF pulses, and they could record significant slowdown of the Rabi-driven oscillations due to the frequent measurements of the system. And here they had a two-level system, and they observed really a freezing of the dynamics, or at least a slowdown of the dynamics due to a measurement. Then the quantum Zeno dynamics, which is a more general effect, was first tested in an experiment 2014, so it's not that long ago, in these two papers, which are also recommended for you as a reading before the talk. But don't worry, so I'm going to talk about these two experiments later, and I don't require you to know already what's written inside. But I will discuss those two experiments later on in detail. And in the beginning, it might be nice to note that in the beginning, the quantum Zeno effect was stated for an unstable system. So for a system which is decaying over time, and that we can really stop the decay of the system by measuring it frequently. And all these papers that I showed you have no natural decay. But so this one was 1990, and then only 7 years later, there were the first experiments really on an unstable system where they could show that the instability is really slowed down, or that the lifetime is enhanced by frequent measurements of the system. And one thing that I want to add also is I recommended you a review paper to read, and there it says that no experiments have been performed so far to check the multi-dimensional Zeno effect, which is the quantum Zeno dynamics. And as you can see here, after this review has been published, there were experiments on that effect. So don't get misled by the fact that they state there have not been any experiments yet. And one more thing about my talk. So I'm going to focus on the physics and not too much on hard mathematics. So I'm going to show you also formulas and derivations of how to describe the dynamics of the system, but I'm not going into very much detail with the mathematical derivations of the effect. And also I'm going to focus on discrete variables, so I'm not going to talk about continuous variable measurements. So let's start with the Zeno effect. So I already mentioned it several times, and I think you already heard about it before, but now I want to introduce it properly. So what is the quantum Zeno effect? To talk about that, we first have to talk about quantum measurements, because we're talking about measurements all the time. So a quantum measurement is the following. So imagine you have an initial state, which is the superposition of two different states. So here, for instance, if we have a qubit or spin system, we can have a superposition of the two eigenstates 0 and 1. And what happens if I want to measure the state now? My meter cannot be in a superposition of two different states, because every time I put like a ruler or some measuring device to my system, it will definitely have some classical position of the lever. So something must happen here. And what happens is that the system collapses into one of its eigenstates. So with 50% probability, we will find the system in the state 0, and with 50% probability, we will find it in the state 1. So we can only have one of the two outcomes in one measurement. And this is also the transition from quantum to classical physics. And there's a lot of discussion about what a measurement actually is. So this goes very deep into philosophy, actually. So everybody has a slightly different opinion on what happens. And one that is also shared by many people, and the main people who also worked on quantum Zeno effect, is that the measurement itself is more or less just an effective description. So we will talk about the projection postulate later, and that everything that happens in between of the superposition and the collapse of the state is just effectively describing what happens in a huge process of coupling the system to a meter to read out the state in the end. So this whole very complex mechanism is just mapped to this mathematical formalism of the measurement. So it does not claim to explain how the measurement is performed, but it just says, okay, here are the tools. That is how you can calculate what comes out of the measurement. And this is also how I'm going to treat it. So I'm not going into the philosophy behind it of how is that measurement happening, but just using the mathematics behind it. So we want to now describe a little bit more in detail what's actually happening in the measurement. So how does this collapse from the superposition to one of the eigenstates go on? And in the beginning, let's say we want to measure something. So what do we want to measure? We measure some observable. And for instance, I wrote here n Hamiltonian or the energy function, but this could be any operator. So we have the operator in some eigenbasis, and then we can take our initial state and we can spectrally decompose it into the eigenbasis of our operator. So you write it down like that. And then we can simply calculate the expectation value of the energy measurement here by simply calculating the overlap. And then we see that the energy expectation value is given by the sum over the eigenvalues of the observable and of the eigenstate. So this is now expectation values. That means that when you measure a lot of times, then on average you will get this result for your observable. Let's go a bit more specific. So what happens if I want to measure, for instance, the ground state of my system? So if I think, for instance, of a harmonic oscillator, so I want to measure the ground state and want to see is my system in the ground state or not. I can use the very same formalism. So I calculate the expectation value of this observable, and this is simply the projection of the initial state onto the state 0. And then we take the absolute square, and this is this coefficient A0 squared. And we can also call this the probability. So this is the probability of the system being in the state 0. But what happens now if we do a single measurement? If I do one single measurement, I will not measure P0. I will measure the yes or no. So was my system in the ground state or not? So what happens is then not that I have this nice expectation value with a p0 in the end, but my state will collapse, and in the end I find the ground state. And the probability for this to happen is, of course, p0, but when I perform a single measurement, I don't know anything about that. I just know, okay, now the outcome was 0, so, okay, the probability is not 0 to measure that, but besides that, I don't know anything. And this process of a single measurement we can also describe a bit more in detail, which is the state after the measurement. And the state after the measurement is given by projecting the state onto the state 0, which we want to measure. And then afterwards, yeah, this is the coefficient A0, and the cat 0 is what's left. This is not normalized yet, so we normalize it. And the normalization factor is actually the probability, and then in the end, after the post-measurement state is 0. So that was now one specific example of how to describe the measurement. So we always talk about projection operators, but it's more or less just the observable that we want to measure, the population of the ground state. So we can sum that up and write down the projection postulate by von Neumann, and this is now for wave function. So we have the probability to measure the like any arbitrary state, so now it's here a j, not a 0 anymore, is given by the expectation value of the projector or the projection of the state onto the state we want to measure. And then the post-measurement state is given by exactly this projection and normalized by the probabilities. We can also do that a bit more general and go to density matrices. It looks exactly the same. So just a generalization, and here the probabilities are not given by the expectation value as in the uppercase, but by the trace of the projection operator and the density matrix. And then, of course, on the right-hand side, we see that the post-measurement state is now given with the projection operator on the left and right, because that's how density matrices are defined. So, now we know something about projective measurements, and now let's see what we can actually do with that. So imagine now we want to measure any observable A, and we have here the eigenbasis of this operator, just as before. And then we prepare our initial state to be in some of these eigenstates. So we just call it here psi0. It doesn't have to be the ground state. It can be any eigenstate of the system, of the observable that we want to measure. Then we have some temporal evolution, because we want to have some dynamics. We want to make it interesting. So we now drive the system. And we assume now that we drive it only for a very short time. That means that we can expand the unitary operator in orders of the exponential function. So for instance, here we have the second order. So the unitary is now not an exponential function anymore, but we have the expression including the 1, the h, and the h squared. And then we can apply this unitary operator onto our initial state, so in the line below. And then we can ask ourselves the question, how large is now the probability that we are still in the initial state? So this is called the survival probability, and the survival probability is given by simply projecting the state after the propagation time tau onto the initial state. And then by simply evaluating that, we find this expression here. And we see that the probability is given by 1 minus tau squared, so the time in between two measurements, over the so-called Zeno time. And the Zeno time is simply defined as given here at the lower line. So if you quickly look at what the state looks like, you already see roughly where this is coming from. So you have an h squared, you have an h. So this is also the variance of the Hamiltonian, if you recognize the formula. So we see that the survival probability is given by 1 minus the time in between two measurements squared over the Zeno time squared. Now we can repeat that. So we measured our system after some finite time tau. And then we repeat this n times. So the total time is given by the capital T, which is equal to n times tau. And then we can write that as P of capital T is equal to the survival probability for this small time interval to the power of n. Then we can simply insert our survival probability, just as given 2 lines above. And then we can do the following. We can replace one of the taus by the expression T over n. because it's simply the same. We have the equation written above, so we don't have the tau squared anymore, but we now have the tau times t over n. And now if you look at that expression, that might look familiar, because you have here 1 minus something divided by n in the brackets to the power of n. And this is the definition of the exponential function for large values of n, or to be specific, in the limit of n to infinity. But since we said, okay, we have a lot of measurements in a very short time in between, this is very close to the exponential function, where we have e to the power of minus tau t over the Zeno time squared. And if we now think again, we have the assumption of very short times between two measurements, so we can calculate the limit of tau to 0 or of n equal to infinity, and then this probability is going towards 1. So we see on the left side the probability for our state to be in the initial state after a time capital T goes to 1 for very short measurements, for very short times in between two measurements. And that is exactly the quantum Zeno effect. So by very frequent measurements of our system and of very frequent observations of our initial state, we can freeze the evolution and let the probability to leave the state go towards 0, or to stay in the initial state staying 0, staying in the initial state going to 1. So this is now one example, and I think it's very nice to see that the mathematics behind is not very complicated, but you can see very easily that you have this convergence of the probability. So let's talk a bit more about the survival probability. So this is the same formula as we've seen before on the slide before. And I want to remind you this is only valid for very small times tau in between two measurements, because we made the expansion of the unitary for small values of tau, so only the second order expansion. Then we can look at how does it actually look like. So here we see the survival probability as a function of time. And for the small values of tau, we are on the left side, so on the left higher branch, so here. And we see that here we have a quadratic behavior. So the survival probability drops quadratic. And if you would follow that line for a long time, we would have this, this curve here, which is indicated by the red dashed line. But what we do now is we measure the states before it has this exponential drop, but we measure it here at this point, and after measuring, we reset the survival probability, because when we measure the system, we know that it's still in its initial state, which means we should start anew. So we know now, again, our initial state, and then we reset the timer, and we have, again, the quadratic behavior. And if we add up all these quadratic behaviors, in the end, we have a not so steep slope as for the exponential function here. So you see this upper function here is much higher than the exponentially dashed line. So the probability of finding our system in the initial state after a large time t is very much increased compared to if we don't perform a measurement in between. And we can think of this, the reason for this being that the transition probability, so the opposite of the survival probability, which is 1 minus the survival probability, scales as tau squared. So the probability to leave the initial state is tau squared, but we perform measurements with a rate of tau to every tau. So and if you have very short tau, then the tau squared is much smaller than the tau. So this is a very hand-wavy argument, but I think it helps a bit the intuition of why this is actually happening. So we just measure our state much more often than it has actually the opportunity to leave the initial state. So then we also have the Zeno time. So if we, you saw before that the survival probability depends on the Zeno time. What is the Zeno time? So on the one hand, I already said it's the variance of the Hamiltonian. But this is a bit hard to imagine, so what actually happens there? So what we can do is we can rewrite our Hamiltonian. So we separate it into two different parts, where one is called H0 and one is an interaction Hamiltonian. And we can do this by defining two different projection operators. One of them is the projection onto the initial state, so the psi 0. And the other projection operator is the projection onto all other states. So it's 1 minus the projection onto the initial state. And then we see that H0 is simply defined as the Hamiltonian matrix element within each of the subspaces. So it is just the elements which are in the subspace, or which are simply the diagonal elements of the initial state, and everything that's within the orthogonal subspace. And then we have the interaction part, which contains all the elements where the Hamiltonian induces a transition from one subspace to the other. So we see here that it's the coupling between the orthogonal subspace to the H0, and here we see that it's the psi0 to the orthogonal subspace. So we have something like an H0 and an interaction term, even though we're only having one system here. But the advantage of rewriting it like that is that we now have the properties that H0 is diagonal in psi0, and the interaction Hamiltonian is the matrix elements are 0. So that means that many elements are actually vanishing, and everything that's left in the end is that expression. So the Zeno time is now simply given as the matrix elements of, or the overlap of the interaction Hamiltonian with the initial state. So this is now simply the expectation value of the squared interaction Hamiltonian operator. You might think, why is that now more handy? Where we can rewrite it. And then it looks like that. So on the right side, I simply inserted a 1. So here in the middle, we have just the basis, the 1, except for the initial state, because you saw before the expectation value with respect to the initial state is 0. So, and this expression now means that we sum up all the transitions from the initial state over the interaction Hamiltonian to all the other states and back to the initial state. So you can think of that as the Zeno time explores all possible intermediate states. So it looks like, which transitions can I take to go from my initial state to some intermediate state and then back to my initial state. And of course, this gives you how good your Zeno dynamics is, because when you have a big overlap with one of the matrix elements, it's very likely that you leave your initial states, because, for instance, when you have an overlap with one state very strongly, then you're probably going to populate that state very quickly. And this kind of gives you the time scale on which you can induce Zeno dynamics, because when your time scale has to be shorter than that in order to freeze the evolution to your initial state. We can compare this to the Fermi golden rule. So this is the rate of transitions from one state. And you see here that written in the same notation that this natural decay rate only covers the resonant states. So instead of exploring all possible intermediate states, the natural decay, so the inverse lifetime of the decaying quantum system, explores all only resonant transitions, so a lot less. So it's a very different, a very similar spirit, but it does something else. So the Zeno time really explores all the subspace. Now you can ask yourself the question, what happens when my variance is actually very large? So what when I populate a lot of states in between, and when the overlap with these different states in the middle is actually quite large? Then you can also say, well, I populate a lot of states which have a very large overlap with my initial state, and then I'm maybe more likely to leave my initial state. And it's actually true that the important part here is not really the measurement, but just the disturbance of the energy levels. So a measurement is disturbing my energy levels, and then it might be that there's more overlap or less overlap with the states. So what I do is I simply measure the state more often so that the overlap cannot become big enough. But it could also be that I measure the state, then I have some feedback mechanism, and then maybe there's more overlap than before. So we can look at that a bit more in detail. So the thing is, when you're very short times between the measurements, and up to now we only considered the limit towards 0, we can do this the second order expansion of the unitary. But when we really have large times in between two measurements or large energy fluctuations, this is not really allowed anymore. So what we can do now is we can look at a more general case. So here I have the survival probability rewritten. So you simply see here I have written the probability as e to the ln p. So this is just the same, just replacing it. And then on the next step I introduced an effective decay rate, and the effective decay rate is simply defined as minus the logarithm of p over tau. So you see I actually didn't do anything. I just rewrote everything such that I have the form that is given here. So I have something like a natural decay or an effective decay rate in an exponential way, but now my decay rate depends on the time in between two measurements, which means it's not a natural dumping from an exponential function, but it looks a bit more complicated. Namely, it looks like that. So this is how the survival probability would really look like. You already saw that on a previous slide, where I showed you that we measure at this discrete intervals of tau, and that we actually gain from this quadratic behavior in the beginning. So here the solid line is the general expression for the survival probability. And this is, first of all, everything you have to look at. So we're going to talk about other two lines a bit later. So we see that in the beginning, we have this quadratic behavior. So we go here really down in a quadratic way, but then we have a more extreme damping afterwards. So now we can consider that our system has actually natural decay gamma 0. So we assume that we have a decaying system and we have this natural decay rate, and then it can be, so it doesn't have to be, but it can be that our effective decay rate at some time tau star is actually equal to gamma 0. So there might be some time where the two decay rates coincide, and you see that in the lower plot. So the dashed line, so the upper one of the two ones, so this one, is this e to the I gamma 0 t. And at some point they cross. At this time here, which is also labeled as tau star. And at the second they cross, the decay rate is actually the same for the naturally decaying system and the survival probability of the measurement. So that means when I measure in this intervals of tau star, then my system actually looks as if it would be decaying naturally. So when I measure in this specific time steps, I recover the natural decay of the system. And we also saw before what happens when I measure in a shorter time interval. So on the left side of this intersection here, then the survival probability is actually larger, and then my decay is slower than the natural evolution would be. And this is called the quantum Zeno effect, as we saw before. But you already see I can also do the opposite. I can also go on the right side of the system, and then I see that when my time in between two measurements is actually larger than this time tau star, then my decay is faster. So I'm actually increasing the decay of my system by performing measurements, and this is called the anti-Zeno effect. So here you have two different examples for a time of for two times tau 1 and tau 0 and 2, sorry. Where I chose a tau which is leading to the Zeno effect or the anti-Zeno effect. So the upper curve of the two is a time where the decay is actually slower than the natural decay. So our survival probability is higher. And the lower one is a time where I waited a bit longer. So in this longer time in between two measurements, my system is actually decaying much faster, as you can see from the dashed line in the plot. So you see here, this would be the natural survival probability. You see that for this large times here, the survival probability is smaller than if is larger than if I would have done nothing. So we cannot only we cannot only slow down the decay of our system, but we can also speed it up. And you see that the time that I wait to perform measurement is really crucial here. So I cannot just measure, but I have to know what is actually measuring fast. What does it mean to measure fast in order to stop the evolution of the system? And one more thing, if you look at the left plot, so I already told you that this upper line here is the natural decay, so the e to the I gamma 0 tau. But there's also this other line, the more dotted line, and you see that the survival probability is converging towards this decay, and this is an exponential decay which has the same decay rate, but it has also this coefficient z here in the beginning. And this is a bit mathematical, so I don't want to go into detail, but it more or less comes from wave function renormalization. So it comes when you really calculate the exact survival probability, so not with second order expansion and stuff. So when you really do it properly, you have to use quantum field theory and complex analysis to derive that equation, but in the end you arrive with that decay. And that coefficient z, which describes your survival probability also for larger times, or more or less just for larger times. So it tells you where does it converge to. And I already said you have to be careful how to choose your time in between two measurements in order to freeze the dynamics or to even make it worse by making the decay even faster. And it turns out that actually the anti-Zeno effect is much more common than the Zeno effect. So it happens in way more experiments that you actually speed up the decay of the system by measuring it instead of freezing it, because in many cases the Zeno time is just very short. And yeah, so I already told you that it's mostly because of the disturbance of the measurement of the system and not only due to the wave collapse. Yeah, I also put you some references here. So because this talk is recorded anyways, you can look at them later on if you're interested. So the anti-Zeno effect was first discussed in 1997. So much later than Zeno effect, or not much, but a bit later than Zeno effect, and then the first experiments were already 4 years later. And it's still studied, so there's a recent experiment involving qubits, which is just 2 years old. So now we can look at some...
Sabrina, can you hear me?
Yes.
I just was wondering if, it's Federico. I was just wondering if there's an obvious relation between tau star and the Zeno time. Was dead, I think.
Yeah, there's not a really an obvious relation. So the thing is, the tau star is more like the real, corresponds to the real survival probability, and the Zeno time is really just the second order expansion. So it could be that they coincide, but it turns out that actually the Zeno time is quite a bad approximation. So for very simple systems, the Zeno time is really giving you some information, but this effective decay is much more important. So I think for most complex systems, this is not as simple as the Zeno time that was given before.
Okay. That makes sense. Thank you.
Yeah.
Also got a question.
Can you switch on your... Do you hear him talking? I don't know.
Hello, can you hear me?
Yeah.
There.
So I want to ask, is there a how-to for which you maximize this anti-Zeno effect? So
yeah. So
it
there
depends on the repetition rate.
Yes, so you can actually, so I'm going to show an example later where we talk about the transition from the Zeno to the anti-Zeno effect. And then you see that the curves usually have like a shape like that where they have really a peak. Okay. So that when you have this specific time, you have the maximal decay of, or the fastest decay of your system, but this can't be generalized. So it really depends on your system and what you're doing. And it's not that trivially named, but there usually is one. But it's also important, I said, if this effective gamma rate of tau star is equal to gamma 0 exists, and it doesn't always exist. So it can also be that this case is not even possible. So it could be that you're always decaying faster or slower, and there's no real transition between the Zeno and the anti-Zeno limit. So it's more complicated than just what I wrote here, but the details would be a bit, too intricate. But just be aware that it's not always the case that you have both regimes. But there were actually some experiments where they could show both the Zeno and the anti-Zeno effect in one single experiment. Any more questions to anti-Zeno or Zeno? I mean, I'm going to talk more about Zeno, but good. We already saw we have already two Zeno effects, more or less. So the Zeno and the anti-Zeno effect. And now we can generalize this even more, and we can look at even more general dynamics. So now consider, for simplicity, if you like, a harmonic oscillator. So if you drive the harmonic oscillator, when you start in the vacuum state, you see some evolution of the population as shown here in the lower plot. So you see you start from the vacuum, and then your population just drives up the ladder, and then you have some superposition state or a coherence state which is created here. Now to visualize again the Zeno effect. So you have you're still driving your system, so you see the red arrow, it's still indicating that you have the drive, but you're continuously or frequently measuring the initial state. So you more or less ask if the system is still in its initial state or not. And by doing that, you really see that here the evolution of the population is freezed. So here at the top of the plot, you see there's still this green line, so you just freeze the dynamics and it's not moving at all. But you can also imagine doing something else. Namely, you can measure an unoccupied state. So here I, for instance, measured the state 2 of the harmonic oscillator, which is not occupied in the beginning. And therefore continuously measure the population of this unoccupied state. I will freeze the evolution in the unoccupied state, which means it will never get occupied. So I build up a barrier here, so my system can never populate this state which I'm measuring. And therefore I'm confining my dynamics now to a subspace of a full Hilbert space. So you see at the bottom now that I only have the oscillation between the ground state and the first excited state, but I'm never passing this barrier. And again, I need here the limit of very frequent measurements. But when I do this very frequently, I can confine the dynamics. So I'm freezing the evolution in an unoccupied state. And this is what we call quantum Zeno dynamics. So dynamics because there is something moving, so there is dynamics, but I still freeze something. So I still freeze the population of the unoccupied state. You can also formulate it differently and not say measuring an unoccupied state, but you can also say I'm measuring subspace which is larger than dimension 1, because the projection onto the initial state being the ground state is a projector with a rank 1, so it's dimension 1 subspace. And when I have a projector which has a larger dimension, I can also project to this larger dimensional subspace. And this is totally equivalent to saying measuring the rest of the subspace or measuring within the subspace. So therefore, I'm using these two formulations for that. But
one question.
Yes.
Oh, go on. So, as a measurement, you could also understand if this energy level couples to some distant transition, right? This would be. For instance,
you mean the measurement? Sorry.
I mean, if it interacts with another quantum system, it's basically measured all the time, right? So,
yes.
So.
Yes, we are actually going to talk about that.
Yeah, okay, so.
Yeah.
Okay, then maybe go on first.
Yeah, exactly. So you're absolutely right. So there are different ways of how to do that, and I'm exactly now talking about different methods of how to induce the Zeno dynamics. So this is probably exactly going to answer your question.
Mm-hmm.
Namely, the first one that we talked about so far is repeated projective measurements. So I have my system and I measure it in frequent intervals, and which are ideally very fast. So this can be visualized by opening the box of my Schrödinger's cat very often. So I open it very often and look into the box if the cat is still alive. So this is repeated projective measurements. And now we can write down the formalism for the quantum Zeno dynamics again in a bit more general way than we did it before for the quantum Zeno effect. So we have here, again, a time evolution operator which lives in some Hilbert space. And then I already said we have a projector which has a larger dimension. Or it could have a larger dimension. So here the trace of the projector is equal to S, so this is defined. And then S is the dimension of the subspace, which I'm considering later. So to which my system will be projected, talking about the Zeno dynamics, as we will see in a second. So we have now the S-dimensional projector, and we assume still that our initial state lives within the Zeno subspace. So within the subspace my projector lives in. Then I have some temporal evolution. So I start with my initial state, I evolve it for a time tau, and then I have the density matrix afterwards. Then I'm measuring my system. So measuring my system means that I'm projecting my state afterwards to the Zeno subspace. So I have the projector, the pi on the left side and on the right side. And I can also combine that. So in blue, you see here that the projector times the unitary can also be written as this V. And then the V is simply defined as the projector, the unitary, and the projector. Because we can simply add it on the right side because we started with the initial state being in the Zeno subspace. So now we only have one map. And what we have to do is to calculate these V operators. And if we have n measurements, we can simply concatenate this v operator. So we apply this v operators n times. And yeah, how does this v operator now look like? We can calculate that. So we insert first in the middle of the brackets the explicit expression for the v operator and take it to the power of n. And then we can calculate the limit. And this is not straightforward, but it's some mathematics behind. But it's not that complicated, so you can look into that if you're interested. But I just show you the result, which is that our v operator converges for large values or for n going to infinity to this expression where we have, again, an time evolution operator, but the Hamiltonian is now different, and is namely the Zeno Hamiltonian. So it's just the part of our Hamiltonian which lives in the Zeno subspace. So we see we have one projector here, so this is general. We don't assume that our initial state is living in the subspace necessarily, but we project our initial state towards the subspace, and then it just evolves in the subspace. So I'm just confining all my dynamics, so there's nothing left which drives me out of the initial state. So this is really the limit. It is not resolving what happens if my time is not short enough, but it's really just assuming that I'm living in the subspace forever, more or less. Yes, so there's different ways to do that, because I told you before, the important part is not really the measurement. The important part is the disturbance of the system. So what we have to do is not necessarily measuring, but we can simply disturb our system, which means we simply kick the box of Schrödinger's cat. So we don't have to open it, we can just kick it. And this will also disturb the cat. I think the cat will not like that. And we can describe all this now in a very similar way. So now we don't have the projection, but we have the unitary evolution during the time tau, and then we have the kick operator. And the kick operator in general is just some projectors and some phases. So we can write it like that, so it's just time instant. And then again we do this n times with very large values of n, and then we arrive at the very same picture. So the limit of that is here again a time evolution operator with the Zeno Hamiltonian, and now the Zeno Hamiltonian is not just one projector, but it's all the eigenvalues of the unitary kick operator. And then we have another contribution, which is n times applied the kick operator. So it looks very similar. So we have some evolution which is confined to the Zeno subspace, and then some phases. But now we can go even one more step further. Namely, we don't have to kick the box, but we can simply, oh sorry, I forgot something. It's actually called the bang-bang control. So you might heard about that before. I know that you heard about it at the Cusco school. And it's actually a special case of dynamical decoupling. So in case you're interested in dynamical decoupling, I put your reference here, where they explain how the relation between Zeno effect and dynamical decoupling is, but it's essentially that. So mathematically, it can be described with the same words. Sorry, now we don't want to kick the cat, but now we want to shake the cat. So we don't apply the unitary kicks, so kicks in a specific time separated by a different time, but we just continuously shake the box. So all the time we shake the box. And this is just a strong coupling. So exactly what you said before. So we now have a Hamiltonian, which is some normal Hamiltonian plus some coupling. And the coupling has here a coupling strength kappa. And this coupling operator is just having, again, some projection. So it's just the eigenvalue decomposition of the operator. And then we have the complete evolution, which is here in the H kappa is now both terms. So it's the coupling Hamiltonian and the free evolution of the system. And it's the very same thing. So you calculate the limit. And in the end, you have the temporal evolution, which is just given by the unitary, with H being the Zeno Hamiltonian. And here now, the projection operators come from the eigenbasis of the coupling Hamiltonian. And indeed, it turns out that all the three methods are maybe experimentally different, but mathematically all of them are completely equivalent in the strong coupling or the vanishing time interval limit. So when I go to the limit and I really say I have infinitely strong coupling or I have a vanishing time in between two measurements, all three strategies are exactly the same. And in the paper that I reference here, they actually show that they just differ in the limits, in the order they take the limits. So if they first decrease the time or decrease the coupling, it's actually all the same. So now we talked about many methods of how to annoying cats, and now we want to see what can we actually do with that. So there's one example, which are decoherence-free subspaces. We saw that with all the methods, we are restricting our dynamics to some subspace of our system. And now I can imagine if I have a large system and maybe one of the highest states is subject to a lot of decoherence, then I can simply say, okay, I'm using the Zeno effect now to simply decouple the evolution of my subspace from the rest of the system. So I can simply say I cut off the state which is very prone to decoherence by using the Zeno effect. So I can, here called fight the enemy, so I can avoid decoherence by using the quantum Zeno effect. And here I have an example, which comes from the paper that I referenced above. So let me explain what you see. You see on the x-axis the time in between the two measurements or the coupling strengths in a re-normalized way. So it's here the bandwidth of the bath, but it's not that important. It's just to make the two quantities comparable. So it's some normalized time. And on the y-axis, you see the decay rate after the whole coupling or measuring process with respect to the natural decay rate. So if it's 1, it's exactly the same, which means we don't disturb the system at all. It's naturally decaying. But if we are below 1, then our induced decay rate or our resulting effective decay rate is smaller than the natural decay rate. So we suppress the decoherence. Or we can also say we have the Zeno effect. If we are above that line, we have an enhancement. So the effective decay rate is larger than the natural decay rate, which can also be called the anti-Zeno effect. And here you see 3 different curves for the 3 different control methods that we talked about. So we have the projective measurements at the bottom in red, then the bang-bang control or the unitary kicks, and on top we have the continuous coupling. And you see that they all do qualitatively the same, but the turning point or the transition point from the suppression to the enhancement region is different. And here, the question that Carl, you also asked, you see there's a peak. So there's some value of the time where your decay is largest. But again, this is not, so it is quite general, but it's not the most general case. So there are still some cases where you don't have the suppression, but for the system they assumed, so they calculate everything through the 2-level system, but they started with a very general setup. They showed that with all 3 methods you can achieve both limits, but for instance, if you look at the red line, the suppression area is reached much harder than for the continuous coupling. So you see here the point where the lines intersect is here at the very beginning for the projective measurements, and here for much larger times for continuous couplings. So it can be that even though you have this time for the projective measurements, you cannot reach it in an experimentally feasible way. So even though it doesn't make mathematically a difference, it makes practically a difference. So how good you can really perform that. So it really depends on the experiment and also on what you want to do, because maybe you want to enhance the decoherence, on which method might be the best for you. And yes, so talking about enhancing the decoherence and enhancing the decay, it could also be that we want that. So maybe we really want to induce decoherence. Maybe we want to learn about our enemy, the decoherence, and we want to induce it and tune it. Then there's another application, which is quantum simulation, which is actually my project. And there the goal is really to use the Zeno effect to induce tailored or to induce tunable dissipation and also non-Markovianity in our case. So for those of you who are not that familiar with non-Markovianity, it's just memory effects between a system and a bath. So we have an open system which interacts with an environment, and if we have some information flow to the bath and coming back, then we call that non-Markovianity. And normally in open quantum systems, you have often the Markov approximation, which just says information goes from your system to your bath and then it's gone, which is usually the case when you have a very large environment, a very large bath, then usually the information is just gone. It can be that for very strong couplings or small bath, that there's memory backflow. So where's the dissipation coming from? So here you see again the equation that I showed you already a few slides before. So this is the measurement process. So you start on the right side, you see with the initial state, you have some free evolution during the time tau, and then you have the projection. And during this step, our state is getting mixed. So if we start with an initially pure state and we let it evolve, there's some finite probability that I'm behind the Zeno barrier, that I'm outside of my Zeno subspace. And when I then project, I will mix the state into the part being in the Zeno subspace and the part being outside of the Zeno subspace. And this is an incoherent mixture, so it's just a mixed state. So this is more or less the definition of decoherence. So I lose information, I mix my state. So this is a step where the dissipation comes in. So we see also here we need the measurement, because the measurement is actually destroying information here. And now what we did in this project is we performed the Zeno measurement and we varied the parameters of the free evolution of the system and of the Zeno measurement. And here we see a plot with the Zeno infidelity. So that means the areas which are orange have a very high Zeno fidelity, so very good Zeno confinement, and the black area doesn't. And you see on the x-axis the strength of the system-bath interaction or the strength of the Zeno interaction. And on the y-axis, you see the strength of the coherent evolution, so the normal evolution of your system. And you see very clearly that when your coupling strength, your Zeno coupling strength, is larger than some value, so for instance like 1 or 2 here, you see that the Zeno infidelity is vanishing. So your Zeno dynamics are almost perfect. And this is exactly this limit of strong coupling, the more or less continuous coupling. But you also see that when you go to the very left of the picture, like when you see here, when you go vertically down the line, that when your beta, so your coherent evolution, the strength of your coherent evolution is getting smaller. So when your field is evolving more slowly, then you can also reach good Zeno dynamics quicker. So this should be for you now a bit of a test if you understood in which directions the Zeno dynamics should occur. So very short times between measurements, or in other words, for very slow evolution of the quantum system, which is on the bottom of the plot, and then also for very strong coupling, which is the right side of the plot. So then I talked about dissipation. So let's look at the dissipation. You see here, again, the same axis, and the yellow areas are closed systems, so no dissipation, and the black areas are very high dissipation. And you see that in the area where we have strong Zeno, so losses from the Zeno subspace, you have a lot of dissipation, because this is actually the area where the measurement is really doing something, so you're mixing your state. And then we also can look at the non-Markovianity. You don't have to get that now in detail, but just for those who are interested, you see that for very specific values of the coupling, so for very specific couplings of my system to the bath, I have strong signatures of non-Markovianity. And then if you look at the 2 lower plots, you see that by moving in that landscape, you can choose how much dissipation you want to have or how much non-Markovianity you want to have. And this is the idea of a quantum simulator. You tune the parameters and you want to generate your open quantum system just as at will. And you could now ask the question, okay, I can tune the one or the other. So if you look at the plots, all the areas where I have non-Markovianity, I don't have much dissipation. That's true, and we changed the model a little bit to make it a bit more complicated. I'm not going to detail, but you see that in the end we can really tune dissipation and non-Markovianity in more or less arbitrarily. So all the red dots that you see here just mean I can reach that. So by tuning my parameters in a sensible way, you can reach all the points that you see in this plot. And this is now a bit more complicated with 2 Zeno pulses, but in general, it's still based on the measurement process, and it's still based on the coupling and the Zeno effect. So we can do really a lot of interesting stuff with the Zeno effect and Zeno pulses. So I talked a lot about how we could do that in theory and how the formulas look like, and I know we also have some experimentalists among the Cusco students, so I want to present you some experiments. So I want to present to you how you can really do that. And I mentioned already before that I want to present 2 different experiments. So we start with this paper here, which is the realization of quantum Zeno dynamics in a Bose-Einstein condensate. And this was actually the first paper on quantum Zeno dynamics. It was published in 2014, so beginning of the year. And the experiment was like that. So we see here, so I go through that step by step. And you see here the Hilbert space of the system. So on top, you see, so first of all, the system that we have is a Bose-Einstein condensate, but more or less it's simply rubidium atoms. So it's atoms, and we look at hyperfine states of atoms. But if you look at the states above, at the picture above, you see it's not that complicated. So also the quantum information people don't have to be scared by that. But it's simply 5 levels at the top and 3 levels at the bottom. So it's an 8-level system, more or less. And you see the evolution that we want to consider now. So I talked about we have a system and we have dynamics and we want to cut it somewhere. We want to induce quantum Zeno dynamics. And that we do in the upper subspace. So in these 5 levels, which are indicated purple. And there you have, so this is the F=2 fine structure manifold of rubidium. And we start in the state 2,2. So this is the MF quantum numbers that vary from -2 to +2. And we assume that we start in the state +2, so on the very highest state here on the right side. And this is also indicated by a spin up. And then the idea is that we induce a resonant drive on the state, on the F=2 manifold. And if we wouldn't do anything, we just would induce a resonant drive on this 5 states, so going up and down all the time, because it's a more or less perfect 5-level system. But now we want to induce the quantum Zeno dynamics into this end. We couple now the state in the middle, the 2,0, to another hyperfine state manifold, so the F=1 state manifold. And here we see again 3 states from MF equal -1 to MF equal +1. And we specifically couple the 2 states 2,0 and 1,0. And you see, because the energy levels are a bit different, we can selectively address this one transition. And by coupling the state, we can perform a Zeno measurement. So we can cut the Hilbert space, as it's nicely illustrated here by this breaking in between of the 2 purple panels. And we can confine our dynamics to the upper subspace, to this subspace here, which is then labeled here accordingly spin up and spin down. So we start with a 5-level system, and by inducing Zeno dynamics, the goal is to make it a 2-level system. So that is the idea of the measurement, so to make things simpler and nice for quantum information people. And this is how it's done. So I talked a lot before about the different methods of how to do that. And what they did in this experiment very nicely is testing all of these measurement procedures. So there are 4 different ones, which vary in discrete or continuous and measuring or not measuring. And actually, before I go into detail with that, I should explain how the measurement is actually performed. So I already told you that this green arrow here, this is a coupling. So it's just driving the population from the state 2,0 to the state 1,0. So this is a strong coupling or a unitary kick. But then we also have this orange arrow here at the bottom, and this orange arrow indicates that there's a decay. So this population in this state is also driven towards some fast decaying states. Then we emit a photon, we measure the photon, and we have a measurement. So we have the 2 different possibilities. We have the unitary driving, which is the green arrow, and we have a dissipative measurement, which is the orange arrow. And by these 2 pulses, we can generate the 4 different protocols. So the first one was the discrete measurement. A discrete measurement is here, so the colors are the same as for the arrows above. A discrete measurement contains driving the system from 2,0 to 1,0, so to the other manifold. And then we measure by switching on the orange pulse, which leads to the detection of photons if there was population. And then we repeat that very often. So here you have the 3 bumps indicating that we repeated 3 times. Then there's the method B, which is continuous measurements. So we continuously leave on these 2 pulses. This means we don't have the discrete measurements in a distance of tau, but we have continuously switch on both, so we're continuously observing our system. So we don't close the box ever again. Then we have the unitary kicks. That means we only have the green pulse. So we don't measure any photons here. We only have the coupling of the higher to the lower manifold using this green pulse. And again, we do this pulse, so it's the unitary kicks, so kicking the box. And then the last protocol is the continuous unitary coupling. So we leave the green pulse, the coherent the unitary pulse on during the whole time, but we don't measure at any point again. So this is the 4 different cases, and they tested all the 4 different cases in the experiment. But before, I want to give you a very short example of a Zeno Hamiltonian, because the system is so easy. So you see on the left side, this is the driving Hamiltonian. We have some Rabi oscillation given by Rabi frequencies omega, and we have a drive between the 5 different states. So this matrix is 5-dimensional, and you drive states transitions between neighboring states. This should not be too complicated. And then you see here the projection operator, which projects to the Zeno subspaces. So it projects to the state, to the 2 purple subspaces. So you have the ones in the first 2 elements and on the last 2 elements, but not on the element in the middle. That means that you project onto the Zeno subspace, which is the one at the top and the one at the bottom. And then you can calculate the Zeno Hamiltonian by projecting your initial Hamiltonian to the Zeno subspace, and you see here all the matrix elements in the middle vanish. So you only drive transitions between 1 and 0, and between between 2 and 1, and between -2 and -1. So just that you have seen a Zeno Hamiltonian. And I think it's, for this example, quite nice because it's quite small and it gives you an idea of how the Zeno Hamiltonian looks like. So now we can go back to our experimental data. So this is a real experimental plot from the paper. So you see here the population as a function of time. The color code is quite intuitive. I haven't written it down. So we start in the spin up, we go down to the middle, and we go to the -2 state here. Then we go back to the +2 state, we go to the -2 state, and so on. So this is a nice, proper Rabi oscillation. Now we perform the measurement. So, and here we now perform a continuous measurement. So it was the method C. And we see that now the population is not going down to the green state or the -2 state anymore, but it just oscillates between the red and the blue, so the spin up and the spin down state. And you have some dephasing because it's a real experiment. You have still some leakage. You have infidelities, so it's not completely closed, but it is very close to a closed system. Now you might ask the question, okay, how do the 4 methods differ now? And it turns out not at all. So here you see, again, the 4 different methods, just the one that you saw before. And this plot, I hope it's large enough, but you see you have the population of the spin up state, so the MF equal 2 state at the panel E, and at the panel F you see the population in the M equal 1 state. And then you have 4 different colors of dots, but what you see is you don't see any difference. So all of them are oscillating, and all of them are oscillating more or less the same. So there's like super tiny differences if you look at them very closely, but the essential picture is they don't differ. So it doesn't matter how you really perform your Zeno measurement. If you have really a measurement, so the intuitive picture of Zeno dynamics or the Zeno effect is that you need the measurements to freeze the dynamics, but it turns out that you don't need the measurement at all. So it works equally good for all 4 methods. But I want to point out this is true for this experiment. So it could be that this is not true for every experiment. It's much likely not true for every experiment. But for this specific experiment, it's true for all the 4 different methods. And this is, I think, a very nice example. And also because the...
Sorry.
Yes.
Sabrina, so in this case, I imagine the reason why there's not difference between the discrete cases and the continuous cases is mostly because they're doing the discrete cases fast enough. Did you do by any chance a comparison for different trigger rates or like repetition rates?
There are experiments doing that, but as far as I remember, they didn't do that in this experiment.
Okay.
I mean, maybe they did that, but I think it's not written in the paper. But it's definitely true. So when you vary the time, it will definitely be that when you have the discrete cases, that it will definitely be getting worse when the measurement is not fast enough.
Okay, cool. Thank you.
Yeah. Anything more to this experiment? Then we can go on to the next experiment, Rydberg atoms. This paper also was published in the same year, and actually just a few months after the first one. And it is also showing the quantum Zeno dynamics, but this time on a much, much larger system. So the system before was just 5 levels, so that was actually comparatively easy. I mean, not experimentally, I don't want to say anything about that, but the system itself was quite small. But now a Rydberg atom has a dimension, when you just look at the relevant subspace, a dimension of about 50. So, and this 50-dimensional subspace is something different. So it could be that maybe it's not working as good or better, or we don't know. So we have now a look at the other experiment, which was actually performed at the Collège de France in Paris. So if you have any questions, you can ask Andrea about that, I think. But let's look at the experiment. So first, I want to explain you how the experiment is set up. So we have a beam of rubidium atoms. So it's actually the same kind of atoms as before, but now in the Rydberg state. And here you see the experimental chamber. So the blue arrow indicates the atoms flying through the cavity. So it's not a microwave cavity, it's just an experimental chamber. So there's no cavity here. So they fly through the experimental chamber, and then you have the green and the red arrows, which just indicates the excitation lasers for exciting the rubidium to the Rydberg regime. So it's not that important for our understanding. And then it's surrounded by some electrodes for creating a static electric field and for generating the RF fields. Because in the end, we don't look at any Rydberg states, but we will look at Rydberg states in static electric fields. And if you remember the talk by Sebastian Glass from the Cusco School, you might have already seen that, or you might remember that. So you see here the energy level manifolds for rubidium or for Rydberg atoms in a static electric field. So let me explain briefly what you see here. First of all, you have 3 different manifolds. So you have the 50, 51, and 52. This is the principal quantum number because so the thing is, Rydberg atoms are very similar to hydrogen because you have a valence electron which is very far from the core. So when they are very highly excited, it almost looks like hydrogen. And therefore, we also have the same quantum numbers. We have the main quantum number n as for hydrogen. And if you would have no external field whatsoever, all the states which you see here for each of the n quantum numbers would be degenerate. So they all would be at the same level, and you would see the scaling as for hydrogen. But what we do here now is we have a static electric field, and then we have the Stark effect. And the Stark effect leads to the splitting of the energy levels for each value of m. So you see on the very bottom of the slide, you see an axis indicating the magnetic quantum number. And you see that for each quantum number, they are splitting up. So the states at the right tip of the 3 manifolds are always unperturbed by the static electric field. And then you see the more you go to higher m states, the more the letters are splitting up, because you have more states per m letter, and the splitting is also higher the higher your quantum number is here. And also the nice thing is that the Stark splitting is proportional to the quantum number here at the bottom of the ladder. So the larger your m value is, the larger is your splitting at the edges of each ladder. So you see that it's proportional. So the diagonal letters which you see here are harmonic. So the transition energies between them is in first order of the static electric field harmonic. So you can assume them to be a large n-level system. So since we have magnetic quantum numbers of like 49, 50, or 51 here, you have a Hilbert space or a spin system which is of dimension around 50. And then you can simply drive, again, Rabi oscillation on this large spin system. So the idea is the following. You start in the n equal 51 manifold. And you can, first of all, neglect the green arrow because it's for probing. But you can look at just the manifold here, so the 51 manifold. And you start at the state on the very right corner of the manifold. And then you apply a resonant driving field, and you will go down the ladder. So you will drive oscillations towards the bottom of the ladder. And when you don't perturb it, it will just look as for the 5-level system, but just larger. And what we do here is then inducing Zeno Dynamics by switching on another coupling microwave field. So the red arrow here induces a very strong coupling between these two states, which are labeled by k equal 2, k equal 5, and the lower manifold. And this strong coupling induces a splitting of the energy levels. So we see on the right-hand side that actually the two pulses, or the pulses, will induce a splitting of the k equal 5 state here. And then the driving field is not resonant anymore. So it's indicated by the gray arrows here at the letter. And it's not resonant anymore. So we are not able to populate the k equals 5 state. So you see, this is an example for the strong continuous coupling and not for the projective measurements. So this is the idea. So we have a large spin system, and we induce Zeno Dynamics by shining in a microwave field which couples one state of the spin ladder to another one. And here you see the evolution of the population, first without the Zeno microwave. So you start in the state on the very right edge, so on the highest state, and then you see here the states which are like the states on the ladder going down, and you're populating all the states one after the other. And on the right side you see also an inset for 3 different timings, but that's not so exciting right now. But now we switch on the Zeno microwave and the picture changes. So you see that again the population in the initial state goes down, but also the population comes back after some time. So you see here the red state at the very lowest panel is the state which we just can reach, but the state afterwards we cannot reach anymore because it is detuned. So we see that the population goes from the highest state to this lowest state, and then it goes up again to the highest state. One thing that I want to stress out here, this is not exactly the same as if I would have just 5-level spin system, because you see that the population of the red curve here at the bottom panel is not equal to 1. So it's not that it's going completely from one end to the other and back, so it's not a complete spin system because the matrix elements are still different. So it's really a different state. So it's not the pure k equal to 4 state is labeled here, but it has still some fractions of the other states. So if you look at the panel 3, so this is the inset. The 3 is the inset of this point of the churning point, and you see many states are still populated, and not only the state at the border of the manifold. And this has the effect that we are creating very non-classical states by doing that. You see here the Q functions of the spin system, more or less, and we see, so if you're not familiar with Q functions, just imagine then to visualize your state on a Bloch sphere. So we don't have the 2-level system, so it's not just one point on a Bloch sphere, but we have some function on a Bloch sphere, and all the points, so the color map on the Bloch sphere indicates how your state looks like. And your initial state is just a Gaussian package as the north pole of the Bloch sphere, and then the RF induces a rotation of the state down the Bloch sphere. So if we wouldn't have any Zeno effect, we would start with a Gaussian package as the north pole, we rotate it down, and then we end up having a Gaussian package as the south pole, and then we rotate again and so on. So this is how it would look like. And now you see how it actually looks like. So here we have the Zeno effect, and you see here we have the simulation and the experiment. And we see at the time 0.76 microseconds, you have some parts on both sides of the sphere. So you see you have something when you have your sphere at the top and at the back, at the front and at the back of the Bloch sphere. So what you do is you're running down, and instead of just going up again, so being bounced from the barrier, you go here, then you're jumping towards the other side of the manifold, and then you go up again. So it's really you go down, you're projected to the other side, and then you go up. And as an effect, you have something which is called a cat state here at this position. So you have a superposition of two states which are on opposite sides of the Bloch sphere. And this is a highly non-classical state. I also have a nicer picture here, which is a different representation. So the first one was the Q function. This is the Wigner function. And you see interference. So you see the color bar goes from negative values to positive values. So it's not a probability function, but it's called quasi-probability function or quasi-probability distribution. And you can have negative values, which are easily said always a signature of quantum effects. And you see here exactly the point where the state is projected to the other side of the Bloch sphere. And you see that you have interference between the side which is on front and the side which is at the back of the Bloch sphere. And the part in the, there is not really a part in the middle, but there's interference in the middle. So you have two parts of a wave function which interfere. And that you can see by this interference pattern at the north pole of the Bloch sphere. So at the top of the picture, you see some red and blue signatures here. And this is a clear indicator for a Schrödinger's cat state. So in this experiment, they've shown that you can induce quantum Zeno dynamics on a very large system. So the size of the Hilbert space, even if we look at the system itself and not at the auxiliary manifolds around which we need to induce a manifold, we still have a dimension of around 50. And then it's possible to not only induce Zeno dynamics, but to create highly non-classical states, the Schrödinger cat states, in this experiment. So I already mentioned two applications, which is the decoherence, no, I mentioned three already, the decoherence with subspaces, the quantum simulation, and the creation of cat states. And I have here a list for you of what you can actually do with a quantum Zeno dynamics. So it is nice and is quite funny to look at, but it's also useful for something. And I put here some papers, so if you're interested, you can look at them. But the rough ideas that you can do with that is state engineering. So we saw that already with the cat states. You created some highly non-trivial state by using the Zeno effect. And you can do something else like tailoring your state of a cavity, or you can create GHZ states. Then you have the creation of entanglement, which is always useful for quantum information, where there's two different examples here. Then we can also protect entanglement. So once you created it, we can also protect it. For fans of quantum computing, we can also generate quantum gates using the quantum Zeno effect. We can study non-Markovianity. So I already showed you in my example that my project that I showed you that we generate non-Markovianity, but it's also in general possible to study the non-Markovianity. And also very strongly related to the decoherence-free subspaces, we can suppress the loss of our system. So this is also just some examples. So there's a lot of papers on quantum Zeno effect and quantum Zeno dynamics, and you can look into them and find many nice things. And now I want to give you a short summary of what I talked about. So the question was that we started with how to fight a weeping angel. So what if a monster attacks you, which stops if you look at them? And I give you many different tools of how you can do that. So the first one is using the quantum Zeno effect. So you just look at it very frequently and freeze the dynamics, so it cannot move anymore. Then you can do the anti-Zeno effect, which is not that smart if you find the weeping angel, but you can look at it and then maybe it attacks you even faster. But maybe you want to do that. Then you have the Zeno dynamics, which means you look somewhere where the angel is not, and then the angel cannot go there. So you can confine the angel, or you can confine the dynamics of your system to a tailored subspace. Then I showed you there's three different methods to do that. So you can either do the repeated projective measurement, so you can repeatedly look at the angel and look back again, but you have to be fast to do that. or you can, well, kick the angel repeatedly, so you do the repeated unitary kicks, or you do the continuous coupling, like with a cat, you just shake the angel and it cannot move anymore. Then I showed you that, well, the analogy fails a little bit here, so we can avoid or induce decoherence of our quantum system, so we can make it decay faster or protect it from decoherence. And I also showed you 2 different experiments where they have implemented quantum Zeno dynamics, and one was a BEC, or it was more very close to just an atomic system with a 5-level system where they've splitted the subspace into 2 different Zeno subspaces, and an example with Rydberg atoms with a very large manifold where they were able to produce Schrödinger's cat state. And yeah, that was what I wanted to tell you about the quantum Zeno effect. And I hope that you liked the talk, and maybe you have some questions that I can answer you.
So, thank you very much for your deductive talk. So, if now you have questions, please just write down in the chat me or your name if you are several ones in your channel. And like this, I can set just the order. I will wait. Okay, then we have first Shaima. Go on.
Yes. Hi, Sabrina. Thank you so much for the talk. It was very nice. Yes. And my question is, I want to, you mentioned that you can sort of freeze the population in certain states. Experimentally, how do you do that?
To freeze the population in different states?
Yes.
Well, very similar to what I showed you in the end. So I showed you the 2 Zeno Dynamics experiments. You're asking for Zeno effect experiments now? Or what is your question?
Yes, okay. I think there was this one particular slide. Now I don't remember. It was actually very much in the beginning. But okay.
So maybe you mean that one?
You go again. So you talk about freeze. So basically, you freeze the population in the states by freezing the time evolution.
Yes.
Yes.
So what you usually do to freeze the dynamics is, performing measurements or coupling it very strongly. It depends a lot on the experiment of what you want to do. And so maybe you mean, let me see.
Yeah, it was, I think, somewhere here. Yes.
Yeah. Do you mean that one?
Yeah. Yes, it was here. Where you said you can sort of freeze the population in certain states and.
Yeah. So actually what I did here, so this is actually numerical simulation and not just pictures. This is what I did to freeze that state is actually to measure the state 1. So I measured the state above, because usually the problem is you don't want to destroy your state doing measuring. So what I said very hand-wavy, you measure the state all the time, but it's actually not that complicated and not that easy to measure a state without destroying it. And for instance, what you can do very often in what is done in many systems is to couple your state to another meta state or an auxiliary state, and then you measure the auxiliary state. So this is then an indirect measurement. So you couple the evolution, and then you know, for instance, that when you find your meter in some specific state, that your system was in that other specific state. So you gain information by measuring the meter. And to this end, you have to induce coupling between the system and the meter, which is exactly the continuous coupling you need for the Zeno dynamics. So by doing that indirect measurement protocol, you can induce Zeno dynamics. So this is one very popular way of inducing dynamics, and the other one is coupling it to some other subspace, like in the BEC experiment, where this state is just naturally prone to decay. So it's just naturally decaying very quickly. So this is, I think, the most common one, 2 common methods to measure a state.
Okay. Yeah, I think I was mixing up the 2 freezing dynamics, which should relate to. Yeah, okay, fine. Thank you.
You're welcome.
Thank you. So now Federico.
Yeah, so I think I have two questions. The first one is about the first experiment that you showed, the bees.
Mm-hmm.
Now, the question it might be obvious. I'm a bit confused. I guess when they show, maybe in the next slide, when they show the populations.
Or maybe here?
Yeah, here, yes, that's right. So they're doing not continuous, but they're doing measurement, right? Is it just that they're doing measurement, they're doing some other form of measurement, I imagine, to get these population values?
Yeah, sorry, I didn't get the last part of the question, but I mean, in principle, they are in this very plot, they are doing the continuous coupling. So they have the green pulse, which you see at the plot above, switched on the whole time. So the green plot, the green pulse is shining all the time, and it's coupling the state 2-0 to 1-0, and by that you have the Zeno Dynamics. But in principle, all the methods are equivalent, as I showed in the next.
Yeah, no, but what I mean is that then as they're doing that, they're also measuring their population in 1 and 2, 2-1 and 2-2,
Oh,
right?
yes.
And that
Yes.
they're doing by some other measurement procedure. I guess
Yes.
the way to interpret that is that they're doing it slow enough that they don't see any Zeno effect dynamics at all. So that you can.
Yeah, so I mean, I'm not sure about the details of this experiment, but I know that in general what they're doing is they just abort the experiment after each of these time steps. So I mean, after each of the red dots, more or less, or blue dots, and measure it and then start again and wait a bit longer. So they just repeat the same experiment over and over again. So it's not that they measure the state 2-2 or 2-1 and then go on with the sequence, but they measure and then the experiment is over, and then they repeat that for different time steps. Because otherwise the measurement of 1 and 2 or of all the other states would affect the dynamics, of course. So sometimes they don't interfere, they abort the experiment, and they have to do a lot of repetitions.
Okay, that makes sense. And then I have another question that actually we can stay in probably this slide for, which is what happens to two-level transitions? Would a two-photon transition be allowed here? So from, for example, 2-1 to 2-1.
Yes, so it depends on your experiment, I guess, because when you have very strong fields, that could definitely happen. And actually, this is really the limit of very short timings, because imagine you have really finite timing in between two measurements, then the probability is, of course, there that you are somehow in the -2 level. So I'm pretty sure that there are some transitions like that. I guess that so usually the driving fields, so the ones going on the upper manifold, have to be quite small in order to the Zeno effect to occur. So it's not that they drive the 5-level system with like full force and then they use in addition the Zeno field, but usually, so in order for that to work, the ratio of the Zeno field and the driving field have to be working. So the Zeno field has to be very strong with respect to the other transitions. You actually can see that quite nice in this plot, because you see what the Zeno field is doing is splitting this state up into two dress states, so the k = 5. And of course, when your driving field is much stronger than your Zeno microwave field in this experiment, then this splitting will be much smaller than the driving fields that drive the population down. So the dress state splitting has to be significantly large enough that you don't just jump over the state. So it has to be really tuned in a sensible way, the field strength, so that it works out in the end.
Thanks, great talk.
Thank you.
So anyone else? I see no. So I have a question actually. So I'm a bit skeptic, let's say, about suppressing decoherence. Like, can we really use that while we are still how to say that? Like, while we are still using our system, let's say, for quantum sensing, for example, we are playing with different state. There is a way to use the Zeno effect to suppress decoherence or no?
I would say it depends a lot on your experiment. In general, I would say yes, but The thing is, of course, you have to induce the Zeno effect somehow, and you said quantum sensing, and the problem is you don't want your Zeno field to affect the quantity that you measure. So I think it's really tricky to combine the Zeno effect and quantum sensing, and as far as I'm aware of, there's no experiment doing that. So like really increasing, for instance, the precision of quantum sensing using the Zeno Dynamics. But I think also because you see this Zeno Dynamic papers are from 2014, so it's not super old. So it could be that maybe there's research going on soon and they can really do that and increase the precision of sensing protocols. But so far it's just complicated enough by itself, I think. But you have to be aware to not disturb anything else of your system. Because you also see here on the right side of the slide that your Zeno field is also affecting the energy levels of all the other states. So you see this green states roughly above the black ones, and therefore your microwave is really affecting also other states in the ladder. And imagine you want to measure the transition now between two states, then of course that's different in your Zeno case and without. So either you have to know what you're doing and calculate out again afterwards, or you have to be really sure that you're not affecting the one quantity with the other.
Okay, thank you. Actually, I have a second question. In the very end, you briefly showed a paper about, just in the list of paper, about entanglement generation. So we can generate entanglement using quantum Zeno effect, the dynamic, right? Yes. Can you quickly develop, or is it like too...
I can't give you very many details on that.
No, just the main idea, not Git.
Actually, I'm really not an expert on that. I think I skimmed over them, but I'm not too good in explaining them right now, I think. But I think the idea is very similar to the cat state experiment. Okay. Because in the generation of the cat state with the Rydberg atoms, so this one, this is not entanglement, but superposition state. But in principle, you can think of your large spin ladder also as a bunch of spins. And then when you're simply having some boundaries where just at the boundary you're creating some superposition or some entanglement of states, that could work. But actually, I think I shouldn't give too much information on that because I really am not expert on that.
No problem. Thank you.
Yeah.
So I see no other questions. So thank you again. It was really nice, and I think we can stop there. So see you all. Thank you.
Thank you. Bye.
Bye. Thanks a lot.